All right, in chapter 7, what we are going to discuss is the problems of finding the distribution of functions of random variables, one random variable or more than one random variables. Okay, so formally, whenever a random variable, say x, is given, then our goal is to find the distribution of function of x. So example will be, what is the distribution of x squared? What is the distribution of, I don't know, log of x is? What is the distribution of x squared plus 2x plus 1, right? So we've seen problems similar to this a little bit so far when we talked about normal distribution. Whenever a normal random variable is given, then we know at least linearly transformed new random variable is still normally distributed with adjusted means and mean and variance. But we are now talking about a general transformation of x, possibly nonlinear, like that. Okay. Also, if we are given a set of random variables, say n random variables, then we might want to find the distribution of a function of given n random variables. For example, if we are given n random variables, then what is the distribution of summation of them? Or what is the distribution of average of them, right? Or what is the distribution of variance of that random variables? Or what is the distribution of, not z, u squared, sum of the squared quantities, right? So those are the possible transformation of given multiple random variables. Okay, so in chapter 7 we are going to talk about several methods or strategies for solving or for finding the distribution of given transformation. Okay, before we talk about the method, let's first think about this question: what do we really mean by finding a distribution of a random variable? Okay, how do you, for example, define a binomial distribution? How would you define a normal distribution? Okay, so one way is find the PDF, right? If we know the PDF of a target random variable, then we know everything about it because PDF tells us everything about the probability behavior of the given random variable, right? Or if you can find the CDF of the target random variable, then you fully define the random variable, right? If you have CDF, you can recover PDF, or if you have PDF, you can recover CDF, right? So if you can find one of these, if you can find one of the followings, then that is the meaning of we found a distribution of a random variable. We just characterize the distribution of the given random variable. Okay, we also can find the MGF. So for example, if we see the MGF of, so for example, MGF of some random variable is looking like 0.2 plus 0.8 to the e to the t to the power of 2, then we actually know this is the MGF for the binomial distribution with success probability of 0.8 and total number of trial 2. So again, MGF was very specific or unique to the distribution. So as long if you can find MGF, then means you found a distribution. You have discovered the distribution of X. Okay, so when it comes to the problem of finding a distribution or defining a random variable of a transformed random variable, that is the matter of finding one of these following quantities, either finding PDF, either finding a CDF, or MGF, okay? So the first technique that we are going to, the first method we are going to talk is called distribution function technique. So what it is we are going to find the distribution of a transformation of X by identifying the CDF of this new random variable Y, okay? So once you've found a distribution function or CDF of this new random variable Y, then you fully characterize the random variable, okay? So again, the CDF of new random variable Y is probability of Y being less than or equal to small y, right? And since we don't have any information about Y, what we are going to do is we are going to use the information from X and reformulate this probability statement and use the density function of X, okay, in order to find the CDF of Y, okay? So let me show you one example, and that'll be the end of today's lecture. So let's consider a random variable X with a density function given in this form. Okay, it's worth checking whether this is a valid density curve. Okay, so let's get a sense by drawing a graph of this density function. So it is defined through this quadratic function, and outside of 0, 1, it is 0. Okay, what we are interested in is the probability density or distribution of X squared. Okay, so when you are dealing with, when you attack through the distribution function technique, the first step is to identify the range of Y. So the range, the word range could be confusing because we call the possible value of X or domain of X as a support, and now somehow we call the possible value of Y not domain but called range. Okay, so you can call it domain of X, a domain of Y. So I would rather say identifying the support of X or possible value for Y that are coming from the possible value of X. Okay, so if X is between 0 and 1, what I'm drawing here is the function Y equals X squared, just to get a sense what are the possible value for Y is. Okay, so by looking at this function, we know Y is gonna still lie in between 0 and 1. In other words, Y will take positive probability over the interval or over the interval 0 to 1 or the unit interval. Okay, outside of 0 to 1, Y doesn't have any positive probability. Okay, remember the strategy of getting CDF? We actually observe all the possible values of the random variable by dividing into, in general, 3 pieces, right? For the values that has no cumulative probability, or the values that has some positive probabilities, or some values of X that have accumulative all the possible probabilities. Okay, so we are gonna still think about these 3 cases where Y has no cumulative probabilities at all. Okay, or having a little bit of probability and then all the way up to. Okay, so let me just make one clean slide. So let's think about the first case when Y value less than 0, then the CDF for y, for this specific y value, negative value, probability of y less than small y, probability of y is x squared less than y. So we know x takes value between 0 and 1, and this y value in this case is negative value, so there is no positive probability for this specific x, so this is going to be 0. Okay, and second case is when y is in between 0 and 1. So again, CDF for this new random variable y is probability of capital Y less than small y. So probability of y is x squared, that, right? So we are going to reformulate this probability statement by taking square root on both sides. So we are going to have this, right? X between negative square root of y and positive square root of y. Okay? Since this probability statement is written in terms of x, we are now ready to get this probability. Let's look at the density curve of x. So we know density curve is positive only 0 to 1. So if you're looking at probability x being minus square root of y, positive square root of y when y is in between 0 and 1, square root of y is going to be somewhere here, right in between 0 and 1, and it's going to be, the negative square root of y is going to be somewhere here. But probability of x in between 0 and minus square root of y is simply 0, right? So this probability is in fact the same as probability of x being 0 and positive square root of y, and we can now get this probability through the integral, right? So 0 to square root of y with density function dx, and I'm not going over the algebra, so this is 3y minus 2y square root of y. Okay, so what we obtained is one of the form for the CDF of y in form of function of y. The last piece is the value y greater than 1. So CDF of y, again, as a probability of capital Y random variable y less than or equal to y, which is probability of x squared less than y, same algebra, y and x square root of y. Okay, but for this specific y, so I'm changing the color, please bear with me, maybe pink. Okay, so this specific y, whenever y is greater than 1, then this is going to be some value outside of this interval. That means we are looking at probability of x being between this entire interval. Okay, let me use pointer. This entire interval. That means we are actually looking at the entire probability. So we know this probability is going to be simply 1. Okay. So as a result, let me write the result on the right upper corner. So, why don't I just make a new slide? So thus, the CDF of y as a cumulative probability for y is in fact 0 for y less than 0, and 3y minus 2y square root of y if y is between 0 and 1, and 1 if y is greater than 1. Okay, so this condition can be slightly different from how I conditioned on before. I am writing this CDF so that this piecewisely defined function can look like a right continuous function, just as a convention. Okay, so by defining CDF of y, we fully defined what distribution of y is. We don't have a specific name for this y, right? Because it's really not specific to any named distribution. Okay. Another thing you can do from this step is just to state the PDF of y, so which is denoted by small f as a derivative. So 3 minus 3 square root of y, which is a derivative of this function, that is valid only for y between 0 and 1. Here I'm being hand wavy just by excluding the endpoint 0. It doesn't matter because it's continuous and it is 0 otherwise. So we could either just finish up by stating CDF of y, or derive the PDF of y from the CDF. So whenever you reach to a certain form of PDF, then you could even find the name of this new random variable y. But in this case, we don't have any specific form for this PDF. So y is just a random variable with density curve, density function looking like that. Okay, it could be really worth to check if this is a valid PDF. Okay, so here's a mini homework. Check if it's valid, just to make sure that all of your work is correct. Okay, so it was quite a lengthy lecture today, but I hope you enjoyed it, and I'll see you in next lecture. Bye.